Okay, so this is problem 68, and this is a great way to review parametric equations that come up all the time in physics or the mechanics, the motion of particles in space, where the parameter is t, time. So, just a general comment. If a particle is free to move anywhere in space, and space has 3 dimensions, it's conceivable that you might need 3 different parametric equations for every dimension. So it might be, you might get a parametric equation, whoops, let me move this down here, x is a function of t, sorry, this is supposed to be an x. X is a function of t, y is a function, well, y would be g of t, and z would be h of t. So you might have 3 parametric equations. The most typical example, though, is, let's say they launch a missile into space, or a missile into the air, or they throw a ball in the air. They're going to take away one of those dimensions because you don't need it. The horizontal distance is obviously going to be x, the vertical distance is y, and so you may see that on a test where they give you, oh, okay, Bob throws a ball in the air at a 45-degree angle, blah, blah, blah. You've seen these problems before, but in calculus, it's important to realize that you may get y as a function of t and x as another function of t, and you might have to find y prime and x prime and so forth. But it's conceivable that they could throw you a curveball and throw in a 3rd dimension, but I think that's unlikely. Anyway, just to be clear on parametric equations and coordinate systems and so forth. Okay, but for this particular problem, this particle is only moving in one dimension, and they're going to call that the y-axis, along the y-axis, along the y-axis. So just one dimension, and so it's still a parametric equation in a sense, but there's just movement in just one dimension. Okay, so that's fine, at least in terms of finding the velocity and the acceleration. As I think you know, that's just going to be dy dt is the velocity, v equals dy dt. That's just going to be 3t squared minus 12. Okay. And the acceleration is the second derivative of y, so d squared y over dt squared, and that's going to be 6t. So that's easy enough. But now they want to say, now they ask you, when is the particle moving upward and when is it moving downward? Okay. To answer that question, it's going to help me to draw a graph. And we're lucky we can make a graph in the Cartesian plane because the spatial dimension is only one, it's y, and instead of having an x-axis as the second spatial dimension, we'll just make turn the x-axis into the t-axis. So now we can graph y as a function of t, so we can visualize it in a way that we're used to. And I don't know what that function looks like. You could graph it if they gave you the if you could use a graphing calculator, but I don't know. It's it's a cubic function, so it might be something like that. The point is, if this is the function, obviously winds up going towards, y goes towards positive infinity as t goes to infinity. So I think we've got the general shape right. The particle is going up when the slope of this graph is positive, right? That means y is increasing. And then it's going to reach a stationary point, or a maximum, if you will, up here, and a minimum down here. So it's going down, y is decreasing here, and increasing here. So the point is, when is the derivative, the velocity, positive, and when is it negative? So that means that we have to find out when it equals 0, because the velocity here is 0 and here is 0 at this maximum and this minimum, okay? So the velocity equals 0, v equals 0 when 3t squared minus 12 equals 0. And so we need to find the solution to that. And there should be two solutions, one for this point and one for this point. And whatever t equals here, y is going up from negative infinity to this point, and going down from this point to this t, and then goes up again. So I'm going to solve that in another video just to help you. I think you could take it from here, but you can double check your answer with mine.